Hello, everybody. Well, today I'm going to talk about a special application of coils, of inductive components, which is a wireless power supply. And the first part of my presentation will be an introduction and some common applications of the wireless power supply, especially in the industrial applications, which is a little bit older than the automotive one. And then we go into the automotive application, where we are today and where we want to go in the future. For instance, maybe the bidirectional approach, and at the end I'm going to give you some constraints, some details about the challenges we've got in the automotive application. Okay, to begin with the history, well, the first one was transferring power through the air via magnetic fields was Mr. Tesla. You all know this person, and as you can see on this, oh, it's not working here. Okay. So you can see the coils, the big coils he was using to bring that bulb to be lightning. So we've got here quite big air gap between the primary and secondary coil of the air gap transformer. And it was quite early at the 19th century. Now we can go to the most common applications of wireless power. On the top you can see that the heat generation, which is very well known in the consumer market and the industrial market. For instance, here the inductive heating of metals and the inductive cooking plates. These are technologies which are using exactly the same circuits we are using too for inductive power supply. It's actually also some kind of power supply, but the power you can get on the secondary part is heat. What we are doing is just to get electricity out of that magnetic field instead of heat. So what we are doing is, for example, like in a charging station of a toothbrush, for example, or for the portable devices, which is done lately in the newest smartphones. So this is actually the lowest power you can think of in kind of such applications, but we are going into the higher powers. What we do is to take a normal transformer, you all know, and then just split the core. You just have to open the core, then you got an air gap transformer. So that's what's happening in the, for instance, in the E-shaped pickup. This is a high power pickup, and the primary winding will be just one turn. This is the blue one. And this can be spread all along the track where you need the energy, for instance. And if you go further and take more of the bigger part of the core away, then you're going to have some simple pickup, as you see on the right side. This is quite simple to manufacture. So this is the principle we got. We got here an air gap transformer. This means we got higher leakage. We got smaller coupling, and we compensate that by using some resonant circuits. This is the actual technology we're using. You see here, these are the possible configuration you can see in the industrial applications. The red points are the primary wires. As I told you, this is only one turn of the primary winding, and the blue devices are the pickups, so-called pickups. This is the secondary part of the air gap transformer. And well, these are the products you may buy. These are existing products since the 90s. The first one is guided pickup by a slot in the, or nut in the ground. The second one is a magnetically guided flat pickup. I'm going to show how it works later on. And then you've got the mechanically guided pickups, which may have a better coupling because in the case of the E-shaped pickup or the U-shaped pickup, you get around the wires, so you've got a higher magnetic coupling and you don't need so much reactive power. We're going to see how this works. For instance, this is a circuit we've got here. This is the system is built out of some power electronics components. We got a rectifier to get a DC voltage from the grid. Then a very simple inverter, which is an H-bridge inverter, to produce out of the DC link a AC voltage, AC square-shaped voltage, and then go into that compensation. This is the clue about the wireless power supply. If you have a small coupling, you need reactive power, not only active power, but also reactive power on the coils. And this is produced by compensation. This compensation is a capacitive part, mostly passive, that leads to increase the reactive power at resonance. So we've got here a resonance system. With a higher resonance, you get high voltages or high currents, and that leads to the possibility to transfer the power to the secondary part. If you don't have those, you're going to get really bad efficiency. You won't be able to transfer high power. Okay, this is the system for industrial applications. This is the whole installation. We got an inverter and a feeding inverter. Then the wires in the ground or even at any location, all along the track, wherever you want to have the energy, you need to have those wires in the ground. These are special high-frequency cables. Well, for instance, Litz wire, isolated Litz wire, and the components you got on the vehicle itself. These are the pickup, which is the secondary part. This is a secondary coil of the transformer. Then you got the positioning sensor, which follows the magnetic field to give the information to the robots. This is your track. You have to go right or left. So you got some kind of a track which is built by the magnetic field. You don't see anything on the ground, but the robot sees the way it's going to have, the path where it has to drive in. And then we've got some data antenna, because wherever you want energy on your robot, you need to communicate with that robot also. So that's why we've got those antennas. We modulate the data on the top of the energy signal. So this is just a higher frequency data transfer on the same wire we're using for the energy transfer too. So now we go into the applications. This is a very old application. This is a crane. It was equipped in Virginia, USA. It was 1998. Just to give you an idea that this technology is quite old, but not really known up to now. So this is a system of 2 times 22 kilowatt. These are E-shaped pickups. So we got a higher coupling. We are able to transfer more power at a certain given volume. A very known application for the automotive people of you. These are the AGVs, automatically guided vehicles. These are the robots following the magnetic field. Okay, so you can see here you've got the pointer is not working, so I have to go over here. Underneath the ground, you got here the wires, which are buried, so you don't see them. But there is the sensor of the car, which is following that path. So you've got a magnetic path. The same for these HEVs too. These are 3 kilowatt supercap charging vehicles. So you've got a supercap on the top to drive over the segments where there is no power, where there is no magnetic field. But most of the time, the vehicle is supplied by the magnetic field underneath the ground. So these are the paths where there is some wire buried under the ground. Now this is also an automotive application, also for the production. We are still not into the car, we are outside the car. But this is for manufacturing the cars. We got here a little bit more of power, high power, 3 kilowatt, for instance, for the flat pickups, and 4 kilowatt for the E-shaped pickup. 4 kilowatt. These are platforms driving around and carrying the parts of the cars. Because also a moving platform on the top of this one, which needs power. So that's why we have to feed power into those platforms. And on the side, maybe you can see that these are the primary wires. So these are on the side of the wall. Now we are off battery. Okay. Further application is heavy industries. So we've got here vehicles carrying high loads, mechanical loads. Then it is also very nice to have such devices because these devices aren't sensible to dirt, aren't sensible to any environmental influences. It's not like sliding contacts. Sliding contacts may get dirty, may get covered by dust or something. So this is very insensible. Can have also rain, can have snow. It doesn't bother because we're using magnetic field. For lower powers, you may have such monorail systems, electric monorail systems for 1.5 kilowatt. This is a very small pickup, right? It's because it is a U-shaped pickup. Just surrounds the cable so that you have a very good coupling, and then the power density is quite high. A very small pickup is the one we're using for sorters, 150 watt. It has to be small because it has to fit into a very low profile. So we've got here 2 wires surrounding this ferrite core. So this is just a ferrite core with some copper on it. And this leads to a good coupling, even though it is very small. And for the higher power applications, there is a very important sector for us. This is the clean room sector, because there you're never going to be able to use sliding contacts, because it's a clean room. For instance, here in Japan, sharp production. Also a higher power application is the elevators. So this is an example of an elevator in Moscow with a big flat pickup. As you can see, this is quite long device compared to the other ones. Well, our benchmark, the highest power we ever transferred with such a technology was 2004, as you can see here. It was in Braunschweig, where I studied for the Transrapid. This is TR09 in Latin. You may know the test track in Latin, and we transferred 2 times 250 kilowatt at a frequency of 20 kilohertz. So it was a benchmark, and it is never met up to now. You see here, these are the primary wires. Okay, also for a railway application, we had a cooperation with Bombardier, and for the rated power of 160 kilowatt, we also transferred over an air gap of more than 120 millimeters, which is also a very high air gap compared to the other ones. We transferred up to 160 kilowatt in a polyphase or multi-phased system. Now Bombardier is using this technology also for other vehicles, for instance, electric vehicles, or electrical buses and electric cars. Yeah, and then we go into the automotive application. So 2009, 2010, we began to work on the automotive solutions to charging electrical cars or hybrid electrical cars, plug-in, for instance, plug-in hybrids. And we had two solutions. The first one we are using was located on the number plate, and the second one at the bottom of the car. The one with the number plate was with in a cooperation with Karabakh in Hamburg. We have two coils of this system. This is the primary coil. This is the pad where you can drive against with the number plate of the car. Behind the number plate of the car, you got the coil. So it's not made of aluminum, surely. This is a plastic number plate, and then you can drive against that charging spot, and the coupling is given by those coils, so you can transfer power easily. We have a very good coupling. From the electrotechnical point of view, it's very easy to transfer the power for this time. But the solution underneath the car is the most wanted, accepted one. So if you got a very expensive car, you don't want to drive against something which is standing over there. So you need to drive over a pad. It's much more comfortable, and for the psychological point of view, it's much better. You can drive over, so you got also the possibility to have taxi stands or something where you don't have to stop. You can drive further and just charge in a certain spot, and the next car will come. So most of the advantages are well known. The charging is going to start automatically. Why? Because the car is able to authenticate itself. So there is a kind of communication between the two pads. We don't need any cables, so there's no hazard with it. The frequency of charging is higher because if you don't do anything for starting the charging process, if the charging process is going automatically, so you don't have to think about it, and then the car is going to be, after statistical computation, the car will be a lot more on the grid than you ever would do with a cable. Because I know myself, if I got a cell phone, I won't charge it even if it's at 50%. I would charge it if it's empty of power. And this is the same with the cars. So mostly if you got the spots at home, in your garage, for instance, and you always park your car in the garage, the car is going to do everything itself. You don't have to take the cable out of the car and plug it in. If it's rainy, if it's snowy, there's no issue with that. You won't have a problem of touching a cable which is wet. You don't have to worry about broken cables and so on, because everything is buried, everything is waterproof. So these are the advantages of those systems. And well, the OEMs, the car manufacturers, want those systems. So we are going to see those systems in the future, maybe in 2 or 3 years. Okay, now we can go a little bit more technical. So this is a overall system. So we got here a grid, the grid front end, which is a normal PFC. If you have a normal system, common cable system, you can have a wire connection, and then you got the onboard charger. So on this part, you got the normal common charger, conventional. You can add components. These are the parts on the right to create a wireless charging system. You add the primary inverter, then the primary and the compensation capacitors. Exactly on the same on the secondary part. You got a coil and a compensation. And then rectify the AC to DC. Then you have two possibilities. You can go directly to the onboard charger, which is very easy because then you got a DC link, but the efficiency is not good. So if you want to have a higher efficiency, you have to bypass that and go directly to the battery. So this is what we are doing now. Now we can go into the coils. I think this is the most important subject for the exhibition today. We got 3 or 4 types of coils which we investigated, and the most common one, whenever there is a publication about wireless charging, you are always going to see this kind of coils. These are the rectangular or circular coils. Well, these are very well-known ones. So you see that this is the secondary coil is a little bit smaller than the primary coil. This is done so because you need some kind of tolerance, positioning tolerance, and if you get a bigger primary coil, then you are able to take a positioning tolerance of maybe 150, 200 millimeters in X and Y direction. Well, the magnetic coupling is not really good because we got here a real big air gap. We're talking here about the typical air gaps underneath the car. So we're talking about 120 to 140 millimeters. And well, the characteristics of the fields, you can see here the field lines, they're going into the middle, and the back door is here. So this is where the magnetic lines, field lines, are going for the back path. So these are the negative ones, and these are the positive ones. So they are not symmetrical. They do not have the same area. They do not have the same ferrite area to get back, and that's what led us to investigate a second variant. This is the solenoidal, or maybe also called bipolar. Actually, there is no unipolar coil. Each coil is bipolar, but you call that bipolar because you got a north and a south pole which are equal. Not like the ones we saw before, not like the circular. The circular are not equal. The north and the south pole aren't equal. But here, there is some kind of a axial symmetry. So you see here, this is quite symmetrical. Also here. So the field is going, the positive direction may be this one, and the negative will be this one. So we got a field which is turning around here. With the circular one, you don't have that. So this leads to a higher coupling at higher air gaps. It's only good for higher air gaps. For smaller air gaps, it's better to have the circular coils. But for this application, it was shown that bipolar coils or symmetrical coils are very good. They've got a higher coupling. We're talking here about 0.15. So this is relatively to the circular coils still good because the circular coils are do have maybe 0.1. So we're talking here about very, very low couplings. Well, the drawback of this topology is that you need some kind of a shielding. So this one, this line here is a shielding. There's an aluminum or copper shielding. Why? Because you got current on the top of the coil. So if this is the smaller coil, if this is the coil on the vehicle, you've got copper on the top because it's actually only a core, ferrite core, and you just have to do some copper around it, so it's very easy to manufacture. But this is a drawback. You've got current flowing on the top of the coil. This means you are going to produce a magnetic field underneath the car. You saw the first coil didn't have any copper on the top of the coil, so you didn't have so much magnetic field. So if you go to this kind of coils, you have to do some shieldings, and this means also eddy currents. Also, a bipolar coil, which has the advantage that you don't have to shield it. This is the double D, but it is a little bit bigger. It is compatible with the solenoidal coil, so that's why we just use it for the primary part, because it's too big. We don't have the room on electrical cars. That's why for the secondary part, we're just using solenoidal, and the primary double D. And this is actually the question, and this is what I'm here. You are the specialist in manufacturing coils automatically. So this coil is not easy to manufacture. And I would be very happy if there are some proposals how to manufacture these coils automatically. Because now we're doing that by hand. Okay, this is too expensive for automotive applications, and that's why it would be very fine if we can talk about it. Okay, just to give you some examples of coils, this is a circular coil having very low field. We had to investigate that, not to heat up foreign objects out of metal, but it was too big for the OEMs. This is the internal construction of the coil. So you see, this is a rectangular you saw at the beginning. The case had some nuts so that you can put the wires inside, and then there was a ferrite plate on the top. The magnetic field is quite homogeneous. This means it could be reduced. So the value of the magnetic field, for instance, the flux density is reduced to a certain amount that you don't heat up the metallic object. So this is a measurement of the coil. You see it's quite homogeneous on the top of the coil. But the OEMs told us, no, this is too big. So that's why the second prototype was 300 times 300, so much smaller. And this one needs FOD. FOD means foreign object detection. So we have to construct also sensors to detect the metals on the top of the coil and switch off the system if something is above it. Now we're gone into the third prototype. This is a 250 times 250 coil. And this is the first prototype we delivered to the OEMs in cooperation with the company Vahle, which is a tier 1 and automotive supplier. The primary coil, as you can see, is 700 times 500. So these are the dimensions of the coils. And to take a look at the electrical part of it, this is the charging characteristic of a lithium-based battery. And you can see we reached the required efficiency, overall efficiency of 90% in most of the cases. Only at very low powers there is a bad efficiency because we got a magnetization current we have to produce on the coils. So this is not like cable charging. Okay, the last point is the bidirectional approach. You can have also the car feeding the energy in the grid. So this is well, a very new approach, which is wanted especially by the government in Germany also. If you've got a car with a big battery on it, it is a big energy storage. If you think of a high number of cars existing in Germany, you may need to use those energy storages in kind of for smoothing the power produced by renewable energies, for instance. So this is the approach we've got. This is the power electronics, quite symmetrical one. We got the inverter and the second inverter on the car. The boards are quite small, so we've shown that it's working, but it's still too early for this. I think it's going to be important subject maybe in the next 5 years. So we've shown that the efficiency is quite easy to meet. We've got here a very symmetrical system, so surely we are able to transfer the energy in the other direction. Okay, I'll go fast now. So these are the automotive constraints. I'm going to skip some for this is the field limitations. These are standards. You have to meet 6.25 microtesla outside the car. We are working on the standardization for this technology. That's why you see here the tables coming from this standard. We got also this sensor I was talking about. This is a sensor for metallic objects on the top of the coil. So we switch off if there is an object inside. This is a field restriction, so we aren't exceeding the fields outside the car. So this is very important. If you have a magnetic field outside the car, no one's going to buy that. We've got also some sensors to detect living objects, living beings, because you have to switch the system if, for example, you've got a baby crawling underneath your car, because there is a magnetic field there, or even a cat having something made of metal, then it would burn. So that's why you have to switch the system if any living being is inside the gap. Okay, because also some positioning assistance. Surely we need some coupling to the primary coils. That's why you have sensors to say to the car, okay, you have to go right or to the left to get on the top of the coils. You got also some actions to have a compatibility with keyless entry systems because they are on the same frequency. So this means there have to be some actions on the power electronics to reduce the fields if there is a key on the proximity. These are the simulations for the magnetic fields, the ISO planes for the keyless entry systems. And this is the sensitivity of the keyless entry system. So you can going to be able to open your car. It's not the problem, but we have to adapt the systems to those keys. So now I come to the end of the presentation. This is the summary. We've got a widespread implementation, well-known, very comfortable, very convenient, compatible with radio systems. And well, we're working on the interoperability of these systems, so we're working with other companies to have a standard for this. And well, one of the outlooks I want to show is the dynamic charging. So this is what we are want to do for the future, to have also a charging lane, as you can see on the right here. Maybe on the street you have a certain line where you can see where you can drive above and get the energy all along the track. So you can reduce the size of your battery or increase the range of the car. Okay, just a few words about the company. We're a small company in Kamen, about 100 millions. Now we are more than 600 employees as a null sheet, 13 subsidiaries and 52 countries, and which is very important, we are 100% family owned, which is very, very comfortable.